Okay, so in this video we're going to continue looking at second order ordinary differential equations, and we're going to start to look at the case where there are two distinct real roots of the solution. So we saw from the last video that if you have an equation where some value a of t is multiplied by the second derivative of x plus b of t multiplied by the first derivative of x plus c of t multiplied by the zeroth derivative of x, and you have some constant d of t or some function d of t, then the characteristic equation you can use to solve this is using the lambda function, a lambda squared plus b lambda plus c equals, and then we have the homogeneous version of the equation on this side here. So this line here is known as the characteristic equation. Okay, so in this video we're going to take a look at a couple of examples where there are two distinct real roots, and we're going to look to find the fundamental solution. So in this first example we're given that the second derivative of x plus 2 times the first derivative of x take away 3 times x is equal to 0. And to be consistent with the terminology, where the right hand side is equal to 0, this is known as being homogeneous or homogeneous. So now we can directly apply our lambda substitution, where the lambda function just takes the derivative. So since this is taking the derivative twice, this will be lambda times lambda, so we have lambda squared plus 2 lambda minus 3, because we're not taking the derivative here, is equal to 0 still. And now we can solve this equation quite simply for lambda by using either the quadratic formula or by factorization. So if we use the quadratic formula, where in this case a is equal to 1, b is equal to 2, and c is equal to minus 3. This gives us that lambda is equal to minus 2 plus or minus the square root of 4 plus 12 over 2. Therefore, our lambda 1 value is equal to minus 3, and our lambda 2 value is equal to 1. And you could have just as easily solved that by using factorization, so you would have had that lambda plus 3 times lambda minus 1 is equal to 0, and then solved for lambda 1 and 2 the exact same way. So now that we have our solutions for lambda, we can use these to find our fundamental solution of our second order ordinary differential equation. So by using the general solution, which I defined in the previous video, when you have two distinct real roots, your x of t value is equal to c1 e to the lambda 1t plus c2 e to the lambda 2t. And then it's just a case of substituting your values. So therefore our x of t in this solution is going to be equal to some constant c1 times e to our lambda 1t, so minus 3t, plus another constant c2 times the exponential e to our lambda 2t, which is just t. And this is what's known as our fundamental solution. And in order for us to solve what the constants c1 and c2 are, we would need to have some initial values. So for example, if we knew what x at time equals 0 was equal to, and if we also knew the first derivative at time 0, if we knew these values, we could then determine what c1 and c2 are. And since our original second order ODE was homogeneous, this means that that would be the final solution, and there are no further steps. However, for non-homogeneous second order ordinary differential equations, there's an extra step involved. So we would need to find our particular solution based on what the right hand side of this equation would have been, our d of t in this example. But we'll take a look at that in a minute. For now, let's take a look at another example of a second order ordinary differential equation with two distinct real roots. Okay, so in this second example, we're asked to solve for x of t, the equation 3 times the second derivative of x minus 7 times the first derivative of x plus 2 times x is equal to 2 times the sine of t. So the first thing you'll notice in this example is that the right hand side of this equation is not equal to 0. Therefore, this is a non-homogeneous equation. Now the first step to solve a non-homogeneous second order ordinary differential equation is to find the fundamental solution. So what we do is we make the right hand side equal to 0 in order to give us a fundamental solution. So then if we apply our lambda substitution and equate the right hand side of this equation to 0, this gives us 3 times lambda squared minus 7 times lambda plus 2 is equal to 0. And once again we can use either factorization or the quadratic formula to solve for lambda here. So we're given that lambda is equal to minus b plus or minus the square root of b squared minus 4ac all over 2a. And in this case our a is equal to 3, b is equal to minus 7, and our c is equal to 2. So this gives us that our lambda values are equal to 7 plus or minus the square root of 25 over 6. So therefore lambda 1 is equal to 2 and lambda 2 is equal to a third. And once again we have two distinct real roots where lambda 1 is not equal to lambda 2. So that means our general solution to this formula is going to be some constant c1 times e to the 2t plus another constant c2 times e to the 1/3 t. And once again this is known as our fundamental solution. However, since the right hand side of the equation is not equal to 0, in other words it's non-homogeneous, we also need to find a particular solution that's specific to the right hand side of the original equation. And once you've added those together to get your general solution, you need to solve an initial value problem to find c1 and c2, like I discussed in the previous example. So in the next video we're going to do that. I'm going to take a look at a particular solution for a second order ODE with two distinct real roots. And we'll take a look at an example as well. As always, thank you for watching, and if there are any questions or comments, please feel free to pop them in the comments box below, and I'll see you in the next video.